Here we go. We're going to finish the second half of Module 13 today. And here's some really good news. The best news you probably ever heard in your entire life. I'm going to say entire life because right now my life is confined to this home. So it may be the best news that you've ever had. We only have one more module to go. We finished chemistry after completion of Module 14. And so after today's lesson, we'll only have 2 more lessons to be finished with chemistry. Did you hear me say finished with chemistry? So I am just as happy as you are. So let's go ahead and get today started with opening up in prayer. Dear Heavenly Father, thank you again for the opportunity to be able to come and reach these students and communicate through media. Lord, during this time, Lord, I just want to give you all the praise. I want to lift you up and all day, every day, find praise. Father, you alone are worthy. There is nothing in this whole world that comes to you by surprise. And let us, instead of feeling sorry for ourselves and feeling confined, let us feel embraced by you in your protection, under your hedge and under your wing. Lord, help us as we go through this chemistry today to have a grasping understanding. Lord, be with each of the students as they get this information on Monday, and bless their week and bless their hearts, Lord. All these things in Jesus' precious name, amen. Okay, so right now it is actually, I don't even know what day it is, I swear, I get so confused. Normally you have markers in your week. Like, we always know Sunday. What?
Thursday.
What?
Thursday.
Oh my gosh. Y'all, my kids are here. I'm with my kids this morning. They're going to be... Can't send them outside yet because they're still doing schoolwork, and it's a little cold right now because today is Thursday the 2nd. And so normally markers, you go to church, we go to church on Sunday. Then Monday we have co-op, so we know what days those are. Tuesdays, it's like, praise God, it's not co-op. And then Wednesday is church day again. Thursday is an errand day for me. Sometimes I try to do, just things that I normally can't do on other days, but normally I do errands on Thursdays. Fridays are therapy. Saturday is just prep for Sunday and Monday. And so, there's markers. So you kind of know what's going on in your week. But since we don't have those, since we don't have co-op, since we're not having church, it's hard to figure out what day it is because we don't have those markers. So hopefully having your videos and all that stuff will kind of still give you markers. I know some of the teachers are doing Zoom and stuff like that. So you do have stuff to do on your day, on your Monday. So maybe you can figure out what day it is. But right now it is Thursday morning, April 2nd at 9:26. That's what time it is right now. But I'm not going to send this video out until April 5th evening. So you'll have it on Sunday night. You'll have it Monday, ready to roll. So, if you have forgotten any of the information that we went over for last week's lesson, you might want to go back and do the last few minutes, or go back through your book, go back through your notes, and figure out exactly what you need to know. Because the things from the first part of this module definitely carry over to the second part. I don't know if you noticed or not, but there's like a bazillion on your own in this module. There's like 12. That's a lot of them on your own, I thought. And but there's a lot of examples. There's 7 examples. The cool thing is a lot of these examples are pretty simple, so we can figure them out pretty easily. But the cruddy part is there's a lot of them, so we're going to go over each of them. So right now we're going to start at the bottom of page 465. So kind of that last lesson, we talked about, let me flip back, we talked about standard enthalpy and finding that standard enthalpy, and you had to look on your enthalpies formation, table 13.3, to figure out that problem. Remember, you had to multiply, you had to look at your number of molecules and then figure out what those molecules were, track the molecules to the table, put them down, multiply, flip them, flop them. We're going to be doing a lot of that in this part too. So hopefully by the time that we get to that section, you'll be able to figure that out. It'll all start to come together and make sense because you're doing the same procedure, but it's just different chemical properties. Okay. Page 465, and there's a lot of reading, so you're going to follow with me with the reading as we get through some of these topics. Okay. 465, midway under applying enthalpy to stoichiometry. This is where we use our grade stoichiometry because a lot of times they're going to give us the grams and you're going to have to convert that to moles in order to compare the moles that we're looking for in the other substances. This is no different than anything that we have been doing since January because that's when we started our stoichiometry. Okay. Are you up, Jack? What? Oh, thought I heard somebody back behind me. Okay. On page 465, midway through that first little paragraph, as we've said many times before, stoichiometry is the backbone of chemistry. Therefore, we try to relate nearly everything that we study in one way or another back to stoichiometry. It's really important. So that's why we do that, because we have to be able to say if we have this much of this, how does it make this much of this? So we have to relate the quantities. Now, example 13.4. We determined previously that the standard change of enthalpy for combustion of ethyl alcohol, that was in the last example, from the previous lesson. The combustion of ethyl alcohol is negative 1,236 kilojoules. How much energy can be produced? What it's saying when it says how much energy, we are looking for the kilojoules. So if we're looking for the kilojoules, we're looking for the change of enthalpy. How much energy can be produced by burning 150 grams of ethyl alcohol in excess oxygen. So that sounds like a really crazy thing to try to figure out. So we got to start with our given, our find, and then go to our plan. The fact that this thing keeps cutting off the top of my head, it's kind of driving me crazy. But see that? That's chips. For some reason, my family stores chips on top of the cabinet. That's going to drive me bonkers. Ignore the chips. If you ignore the chips, it'll ignore you. You know, your mom always says about bees and stuff like that. Ignore it and it'll ignore you. Or your daddy says that. Your mama doesn't say that. Your mama says SWAT like you're a ninja. Okay? So, but anyway. So, what we're looking at on the bottom of page 465 is our question. I hate that our question is split up there. So what we're looking is first is our given. Let's see. Let's start over here. Our given is our standard change of enthalpy is negative 1,236 kilojoules. Okay, because it's negative 1236 kilojoules. Is that endothermic or exothermic? The negative makes it exothermic. Remember that. Therefore, it's going to be in the product. And it also gives us 150 grams. Of C2H6O and in excess oxygen. So now we need to find the energy produced and remember when I said energy produced, I'm looking for what my terms of energy. And in this term, it's going to be kilojoules. I'm looking for the kilojoules that are produced. So let's first start. We're going to have to balance this equation, okay? Because it tells us that we have a combustion. So we know that we're going to have to add oxygen, and then it's going to have to go to CO2H2O. So let's go. Oh boy, I hate that I'm running out of room here on this. So I'm just going to start down here. And I'm going to use a blue pen so that we can have some differential. I really hate that. Okay. C2H6O. I'm going to have to, it's combustion plus O2 produces CO2 plus H2O. All right, now I have to balance this. So in the balancing, you know how to balance these equations. I'm going to write in the amounts, okay? That just makes sense at this point. I don't need to use all of this space balancing equations when you know how to balance equations. So let me make sure you can read that. Can y'all see that right there? I know there's a glare on the board, but it's morning and there's light coming in the window. So what I'm going to do is I'm going to go ahead and write in the full balanced equation. There's 3 oxygen. I think there's 2 CO2s and 3 waters, if I'm right. Yes. Now, it told me that I've got negative 1236 kilojoules here. That's part of my given. Because it's negative, it's going to be exothermic, meaning that it's going to be on the product side. So kind of like we did before, 1236 kJ. Okay? Can you see that? Okay. So now, we have that portion of our, we've already balanced it. The second thing we had to do was put the energies in place. All right, so now we just have to figure out the stoichiometry of it. I'm going to try to, maybe I can move my camera. Hang on. That looks a little better. I figured if I move my camera, then I'd be able to see the board a little bit better and also be able to move around and not stand completely in front of it. I put this little rag right there to keep it from sliding on my stove. Yeah, okay, I think that'll work. You'll just get a really up close look at me. So anyway, let's see. So now we've written everything out, including our energy here. So we know that the energy is going to be released in the product. Now we can start doing the stoichiometry. What I need to do is convert the amount of ethyl alcohol into moles. So this is my ethyl alcohol. Remember that when I'm writing stuff down, that I always want to write down my given first. Remember that my given goes right over here. So this is going to be 150 grams of C2H6O over 1 times, remember right here is what I'm looking for. And what I'm looking for is the energy produced. I'm changing it over to moles. So on the very top, I'm looking for 1 mole C2H6O. And on the bottom here, remember this is where I use my AMUs. So I have to look at that C2H6O, carbon times 2, hydrogen times 6, and oxygen times 1. Oxygen I know is 16. Hydrogen I know is 1.01, so that's going to be 6.06. Carbon, I cannot remember off the top of my head, is 12 apparently. Yes, carbon is 12, so that's going to make that 24. So when I add all of these together, I'm going to come out with 46.1 because the 6.06 is going to round to a 0.1 there. So it's going to be 46.1 grams. Remember, because anytime you have AMU, it's going to be grams per mole. So 46.1 grams of C2H6O per 1 mole. And I got my handy dandy calculator. Willie, oh, you look so cute. He's got a milk mustache. He's eating his cereal. Would you please go over in my crate? There's a little gray, white, blue calculator. Be a lot easier than having to open my phone every time I need to use it.
Is it in a pocket?
Yes, it should be in a pocket. Got my calculator. So 150 divided by 46.1 equals, thank you, my buddy, equals, mark out my grams, 3.25 moles of C2H6O. Okay, so now that I have that, I need to convert that back over to my energy because I've got moles. Now I need to convert that back over to my energy. Now, according to the equation, look at the top of page 466, about midway through. According to our equation, 1 mole of C2H6O will give us 1,236 kilojoules of energy. Therefore, the stoichiometric relationship here is 1 mole of C2H6O equals 1,236 kilojoules. Given that relationship, we can take the 3.25 moles of C2H6O and multiply that times 1.236 kilojoules over 1 mole, because I just told you that the relationship is 1 mole to the 1,236. So if I give that, I just multiply that, and that's going to give us 4,020 kilojoules. Oh, that says grams. Joules. Okay? And that's it. That's the energy that we're looking for. When we're given the grams, we have to find the moles because we know that the moles are related to, I looked at my son and totally lost my train of thought. Because we know when we're given the grams, we have to convert to moles because we know that the moles are related to the energy. Okay? So This is our example. There will be one of these, I believe, on your test. And I'll actually go through your test at the very end of this video and kind of give you some information. I'll be sending your test by Google Docs. So you'll be able to print that off at home. And this week you're going to have very specific instructions. I will be grading this test this week, which means, oh, look over there. Say hi. So I will be, let me do that, get them out of the way. Come on, step out. I'll be grading your test this week. So when you take your test, I want you to scan it and send it to me by email. I'm going to be keeping a file of all the emails I receive. If you say to me, Miss Brandy, I cannot scan this work. My scanner's not working, or I don't have a scanner. Well, I know that either you or your mamas and daddies have a cell phone. And this is what you're going to do. If you don't know how to scan it, on a computer to scan it to, on a printer or a scanner to send it to me, I want you to do this. Listen, this is important because this is how I want your work this week. There is an app called Genius Scan. I'm going to pull it up here. It's a PDF scanner. Can you see that? That's what it looks like. Okay, you can get that. It's free. You don't have to pay for that. But I need you to use that if you cannot figure out how to use your scanner, or if you don't have a scanner. Take that, open it up. When you open it, let's see if I can get it. When you open it, if you go right down here to the camera, then all you have to do is take your camera, point it down at your piece of paper, and it'll have this little yellow box that runs all the way around your paper. And it'll take a picture of just the paper. It's too bright. You can't really see the screen. But on here is some stuff that I've written down. So then on the bottom, it has a little share button. And so you just send it to me at biologybybrandy@gmail.com. Good morning, Jay. Send that to me, and that's how I'm going to get your test this week. And I also want you to send your on your owns to me. So I want you to send the on your owns, and I want you to send the test to me. It'll be assigned on April the 6th, and I know that we would typically be out of co-op on the 13th, but I'm asking you to send it to me by the 13th. So if you do it on Monday, then send it to me on Monday the 13th. If you do it on Friday, send it to me on Friday the 10th. That this work is due on April the 13th, whether we're in co-op or not, meaning have the week off for Easter break. You're going to be doing the work the previous week, and I want the work for that week. So go ahead. It's not like you're doing school that day. You can still have a break, but I want you to send it to me. Either send it to me somewhere between the 10th and the 13th. That's important. I want you to do that because I'm trying to get everybody to keep their work turned in on time. because otherwise I'm getting work several days scattered. It's hard to grade. It's hard to, when I have everybody's work all at once, it's easier for me to deal with. Everybody's is there. I put in their grades and I don't have stragglers coming in. Since we have to do school this way right now, this is the way that I'm asking you to do it. It's not hard, but I want you to have it into my email no later than 5 p.m. on April 13th. If like I said, but I'm going to give you from the 10th to the 13th to get it put in. I know that it's Easter weekend. Nobody's going anywhere. Nobody's doing anything. Please get it to me by the 13th, 5 p.m. If not, it'll be counted late. So it's 5 points off your total. Don't do that. All right. That aside, now we're going to move. We're going to skip some diagrams. I'm not crazy about the diagrams, so therefore 13.8 on your own, you can skip that one as well. And I am going to make myself, let me get a pen. I'm going to make myself a note on here that I have let y'all skip that. I'm making a note in my book. Skip since no diagram. So, skip 13.8 on there on your own. Here's the deal. If you don't watch these videos, then you're not going to get any of this information and you're going to be behind. So I'm really giving you some hefty information during these videos. All right, now let's go to the bottom of page 470, straight over into 471, and we're going to talk about entropy. It's part of the second law of thermodynamics. The first law is energy cannot be created or destroyed. It can only change. So here's the trick. You're going to hear me go through this next part. You're going to hear me say a lot enthalpy for entropy, or vice versa, because they're going to overlap here, and those words sound an awful lot alike, and it's hard to say the right one. So I'm just going to have you follow with me here and show me some grace, because y'all know I mix up my words all the time anyway, because I barely speak the English language. So help me out here, show me some grace, and I'm going to try to get it right. And if I do, woo! So here we go. 470, second law of thermodynamics. First part of that is you have to know what entropy is. Entropy is the measure of disorder that exists within a system. Read right below that. Since entropy is a measurement, it must have units. Now, these units are going to be written in one of three ways whenever you're doing a problem. It's going to be written, again, they chose a letter. I don't get it, but that's what they chose, and that's what you got to know. They chose the capital S as part of entropy. So entropy is abbreviated capital S. This board erases a lot better than the one in the classroom, but it's little. Okay, so entropy equals S. This is change of entropy. Entropy, see, there you go. This is change of entropy. And just like with the other, this is the standard change of entropy. All right? So these are the signs that you're going to be seeing in this section of the part of the module. Since entropy, see, I think I said entropy again. Did I? I don't know. Anyway, since entropy is a measurement, it must have units. These units are always energy units divided by moles and Kelvin. So what it's going to look like, let's start with this one. S equals joules over moles times Kelvin. It can also be displayed as kilocal moles times Kelvin, or kilojoules moles times Kelvin. It can be, can you see that? It can be either of those three when it's giving you the energies, okay? So you just need to look at those and see what it's asking for, but it's going to be in the same way of figuring it out that we've had in the past. Son. How's that? Gotta have my coffee. Y'all know that. It's my drug of choice. Okay. So, entropy is a measure of the disorder that exists within a system. So you can read a little bit more beyond that. I will tell you that there is an example in figure 13.3 in your book. This example is not an accurate example. It's not your best example. When they made this book, as we've talked about 100 times, there are several errors inside of it, and there is a whole website that is devoted to the errors in this book. And they tried to do, when they made new editions, they tried to fix some of those errors. And so in some of your books, it's fixed, and in some of your books, it's not fixed. And in some of your books, it's fixed, but others are wrong. So we just kind of work through the rights and the wrongs. But this example, the figure 13.3, it does show disarray. It does show disorder. But this marketplace on the left-hand side, it says low entropy, meaning that everything's in order. Marketplace in high entropy is where things are scattered and messed up. Well, like I said, that's not the best example because I could go right back in here and clean this up. That's not how entropy works. Entropy doesn't tend to go backwards. Okay, so we're going to talk about that in just a second. Turn your page to the second law of thermodynamics, 472. The second law of thermodynamics is entropy of the universe must always increase or remain the same, but never decrease. That makes that picture not the best example because it'll mess up, but we know that it's not going to stay there, and they're not going to leave all that crud all over the market floor. Nuh-uh, they're going to clean it up. So that would that would decrease the entropy. So that's not the best example, and that's okay. They tried. But anyway, now read the first paragraph beyond that with me, 472. Think for a minute about how this law would apply to a vase. If a vase shattered, and it were to spontaneously rearrange itself to be a whole vase again, that would be super cool. I have a bowl right now that needs that. It would be going from high entropy to low entropy. This would mean that the entropy of the universe would decrease because the entropy of the vase decreased. This would violate the second law. That's why broken things do not spontaneously fix themselves. I know a few people that need to be fixed. There's one. I think I'm funny. Okay. And I like my new island. My husband built me this island, and it rolls around, and it's huge, and it's so cool. I just love it. Love it. Okay. Middle, page 472. As we said before, entropy is a measure of the disorder in a system. As a chemist, you should be very comfortable in determining whether, because you're a chemist, you should be comfortable in determining whether a given state represents high or low entropy. In the case of the vase, see, I think it's funny because I rhymed. It was rather simple to determine which state was high or low entropy. However, there are more subtle differences in entropy which we are about to be made aware. Now, the entropy of a substance changes when the substance phase changes. Okay. Now, think about how we talked about from one of the first days in class when we talked about molecules inside of things. We talked about it last week too. This microwave is a solid. It's a solid piece of plastic. Really expensive plastic, by the way, but it's a solid piece of plastic. Everything looks steel. However, we know that it's vibrating, all those molecules, but they're packed close together. So it has a lower state. Is this correct? Am I telling y'all something right? Yes. It has the lowest state of entropy. So then when we talk about liquids, so solids, they're together, but they're still vibrating. You just can't see the vibration, okay? But then we have liquids. Liquids are a little more fluid. The molecules are moving around a little bit more. And because they're moving around a little bit more, it increases the entropy. It increases the disorder. Things are not like this. They're fluid, man. Okay? But then we have gas. Gas is the highest form of entropy because it's crazy. Gas goes around all the time. It's crazy stuff. So it's floating and it's random and it's doing this. Gas has the highest state of entropy. Solid, low. Water or aqueous, liquid, fluid, medium kind of entropy. And then we have crazy entropy in gas. Okay, so blue section of your page 472, the solid state that has the least amount of energy associated with it, the entropy of a liquid state is higher, and the entropy of the gaseous state is the highest of all. Now, the entropy of a system will increase with increased temperature. Well, duh. We know that if we put some energy to it, the energy is going to cause some disorder. So, if I put some energy, I don't have a lighter. That's my lighter drawer. It's okay, Abby. I don't have my lighter, but if I have my lighter and I lit it up underneath this plastic, I'm going to increase the energy because it's going to turn to liquid. It's going to melt, okay? So, by adding energy, it increases the entropy. Okay, making sense? Okay. 473 blue part. The entropy of a system increases as the matter it contains increases. A sample of gas that has 5 moles or more of entropy than a sample of the same gas with only 3 moles. The more stuff you add to it, the more disorder. Okay, this house, not this house, but I used to have a house that had 2 people in it, me and my husband. Then came a third. Then came a fourth. Then came a fifth into this house. By the time there are 5 people, the entropy increased above the 2. The chaos ensued. And the entropy, see, I just did that. Entropy increased. So chaos took over, took us to like a liquid state. But then we added 4, 5, 6, 7, and 8. What are we thinking? We got up to 10 people living in this house, and it is a constant state of chaos. I don't know that it'll ever be restored, so that might be the second law of thermodynamics. It never decreases. So, get it? The more you have, the more of a substance in that matter that you have, the more entropy you're going to have. That helps us figure out in a chemical reaction what side has the greater entropy. Now, okay, look at page 473. the larger paragraph below the little blue section we just read, enthalpy is very hard to measure. Imagine that. Whereas the change of enthalpy in a system is easier to measure. Change of enthalpy. That's right. He said tropy. I'm doing it again. Entropy. That's why I said this is hard. They should make those words differenter. They should have made them more differenter. Okay. Entropy. I need to have my scholars standing around me. Enthalpy. Actually, I was right. It was enthalpy. It wasn't entropy this time. Now that everybody's totally confused, let's go rewind and do it again. Enthalpy is hard to measure, whereas the change of enthalpy in a system is easier to measure. The same thing happens with entropy. The chemists are usually more interested in the change of entropy than they are in just the entropy. In fact, we can even restate the second law of thermodynamics in terms of the change of entropy. Entropy, the change of entropy in the universe, has to be greater than zero. In order for it to happen, it has to be greater than nothing. Okay? If the entropy of the universe must always increase or stay the same, then the change of entropy has to be greater than zero. You can't go from nothing to less in this situation. Okay? So we have to find out if these reactions are even possible, because what it's saying is that in order for it to meet the needs of the second law of thermodynamics, that it has to be greater, that it has to be a positive or above zero reaction. So right now it's teaching us how to determine the sign, if it's going to be positive or negative, if it's possible or impossible. Determine the sign of the change of entropy for a chemical reaction. Last paragraph in this page 473. To determine the sign of the change of entropy for a chemical reaction, all we have to do is look at the number of molecules or atoms. Remember I told you 2, 10. 10 is greater than 2. The entropy is going to be greater in 10 than 2. So, look at the module and also look at the phase. So we're going to be looking at two different things. First, the number of molecules, and second, the phase, solid, liquid, or gas, or aqueous. So that's in here as well. So let's look at example 13.6. I think this is a lot of fun. I'm going to write this one on the board. Zinc. Let's erase this part. I've got zinc, and it is in a solid form. I have hydrochloric acid in an aqueous form. And it produces zinc chloride, H2. ZnCl, and I'm going to put that right down here, aqueous plus H2 gas. So, if I'm looking at the phases, and I know that solid's low, and the aqueous or liquid is higher, and then gas is way higher, and I'm looking to see if it's positive or negative, then I'm going to say that my solid is low. See my L there? My aqueous is medium. Aqueous, medium. Gas is high. So this is going from a state of low entropy to a higher entropy. So because it's increasing in the product, that is going to be positive. That is going to be on the positive side, which means that it is viable. Let's look at the next one. let's see. Nitrogen gas plus 3 hydrogen gas produces 2 ammonia. Did I write that right? No. Knew that wasn't right as I was writing it. And that would be gas. So, I've got gas, high, gas, high, gas, high. They're all gas. How am I going to determine if it's positive or negative? How am I going to determine if the energy goes up? I'm going to count the molecules. Nitrogen has 1 molecule. 3 hydrogen, that's 3. 2 ammonia has 2. 1 plus 3 is 4. I know it might be hard math. This side has 2. This means that it's decreasing, okay? This means that the entropy is decreasing. So the sign for this one is going to be negative. Can you see that with the glare? All right. Now let's do one of the on your owns. How about we do 13.9b, because it's short and I can fit it on this board. 2H2O, I'm going to guess that well, it's gas plus O2, pretty, gas produces 2H2O2 gas. So now I'm going to look first at my phases. Gas, high, gas, high, gas, high. They're all gas, so that means I've got to look a little closer and count molecules. 2 water, 1 oxygen, and 2 hydrogen peroxide. 2 plus 1 is 3. So we're showing that it decreases. If I'm looking at positives and negatives, then I'm going to say that 3 is greater than 2, so this decreases. So it's negative. You have one of these problems on your test. Now, there's more than one way to find this. If I'm asking for the sign, I'm looking at the gases, the liquids, the solids, I'm looking at the phases. But if I am asking for the sign, I could also be looking for the number of molecules. But could be asking for more than that. I want to be more specific. If we need more information than just the change of sign, there is a way to determine the change of entropy. You can use the equation that's very similar to what we have worked on before, calculating the entropy. What we had worked on before is calculating the enthalpy. And you know, where we took the product, the sum of the product minus the sum of the reaction. Same thing here, except we're just looking at different amounts. We have a whole new table for that to figure that out. And the equation for that is 13.5. On your test, it will tell you which equation goes with that problem. That is a very big help, since all of this tends to be confusing by just looking what we're asking for. If I just ask you for something random, a certain type of energy, you may not know which equation to put it with. This gives you the equation for each problem, okay? You do have access to your book. In your on your test, it also tells you that you can reference page 610 and 612 in the back of your book. On the Apologia test, it does the same thing. It gives you the references and the equations. I help you out a little bit more by telling you which equation fits which problem. So that'll be taken care of for you. Now, look at page 474 at the bottom. It gives you that equation to figure out the standard change of entropy. And note that the table that it gives you standard absolute entropies, and that it's in joules per mole times Kelvin. Okay, joules. So that's important to know because some problems might throw a kilojoule at you, and this is just letting you know that this in the standard form is joules per mole per Kelvin. Okay, times Kelvin rather. So the equation 13.5 is the standard change of entropy equals the little e means sum of the standard entropy of the product minus the sum of the standard entropy of the reactants. Remember, in these situations, you have to flip-flop it. And it's going to give you a positive or a negative number. Same as the positive and negatives just by looking at the equation. When calculating, at the very bottom of the page, when calculating the change of entropy, the S of the element is not 0. Remember, it has to be above 0. So in table 13.4, all of your numbers are positive numbers. Notice a few things about this table is written in the paragraph below the table. The entropies listed here are all positive. This is because the table does not contain values of the change of entropy. It is just the standardized entropy. As a result, they must all be positive because all substances have some level of disorder, which means that they have some absolute entropy. Second, notice that compared to the values of the change of enthalpy tabulated in the table, these numbers are very small. The table 13.3 contains numbers with the units of kilojoules per mole, whereas the numbers here are joules over moles times Kelvin, which means that these numbers are about 1,000 times smaller than the ones listed in table 13.3. So let's look at, on your own, 310. Let me see if I actually wrote that down. I did. Okay. Oh, good. I don't have anything on there. All right. On your own problem, you're going to use 13.5 equation, and you're also going to use the table 13.4. So the equation is CaO in the solid form plus CO2 gas produces CaCO3 solid. Now, if we've just looked at the phases, we would be able to tell that the sign for this is positive because we have a solid and a gas on this side, on the reactant side, and the product side is just a solid. So we're going to know that that sign is positive. Good morning, Sarah. She walks in a room dancing. So now let's work this out according to the equation. The equation, which I'm going to write down here, kind of abbreviated a little bit of that. I think you can see that. And we're going to use this equation to work this out. Now, but we have to use the table. So first let's find CaCO. No, CaO, sorry. CaO in a solid form is 38.2. And that is going to be written as joules per mole times K. And there's one mole of this. We know there's 1 mole because there's nothing written here. The second one, I'm going to write in brown, is CO2 gas. So let's look it up there. CO2 gas on the table is 214. There's 1 mole times, what did I say? 214. 214 joules per mole K. Okay. And that produces CaCO3. Found that one. And that's in a solid. CaCO3 is 92.8. Can't get my thing on. 1 mole times 92.8 joules per mole. Okay. Now what I'm going to do is I'm going to put this in my formula here. So the product, 1 times 92.8, do 92.8, and then I'm going to subtract the sum of these two. So get out my handy dandy calculator. It's going to be 38.2 plus 214 equals. Did I do that correctly? Yes. Was that 92.8 or 92.9? 92.9. This should have been a 9. So 92.9 minus 38.2 plus 214 equals 25, 252.2. Is that correct? 252.2, yes. And that's going to bring me to 92.9 minus 252.2 equals 159. So let's see that it's negative 159. So my standard change of enthalpy is going to be negative 159.3. Okay, all we're doing is doing the same formula that we did on the other ones, except we're doing it into change of standard entropy. All right, so I think that one's kind of easy because we've still got the same formulas that we've had. Now, let's look to our next section. The proper application of the second law of thermodynamics. Warning, this section is a read. So I'm going to read it to you. Please follow with me. If you're just sitting there twiddling your thumbs, you may miss something. What happens to a bucket of water if left outside on a cold day? it freezes. As we learned earlier, the solid state of matter has lower entropy than the liquid state. When water freezes, it goes from a more disordered state to a less disordered state. In other words, for this process, the change of entropy is negative. This, on the surface, seems to violate the second law of thermodynamics, which states that the change of entropy in the universe must always be greater or greater than or equal to 0. The process of freezing water only seems to contradict this, but it doesn't. It's only part of the process. You see, when water freezes, it affects the molecules that surround it. So remember when we had talked about this before in some of our experiments, we talked about the reactions and the trapped gas, the surface gas, surface tension that we talked about several weeks ago, even months ago. This is the same kind of idea here. Think about it this way. When water freezes, its molecules slow down and they don't move as much as they did in the liquid state. This means that they lose energy. Well, where does the energy go? It's released into the surroundings. As a result, when water freezes, its surroundings heat up a little bit. This may sound weird, but nonetheless, it's true. The very process of freezing requires a release of energy. When a system releases energy, its surroundings heat up. So when water freezes, the things surrounding the water heat up. What happens to a substance entropy when it heats up? The entropy increases, resulting in the entropy of things surrounding the water. This increase of entropy of the surrounding offsets the decrease of the entropy in the water. As a result, the total change of entropy of the universe, water and its surroundings, does not change. This is in agreement with the second law of thermodynamics because it says that the change of entropy can be positive or 0. When we look at this process in terms of the second law, we must look at everything that it affects. This is a big deal. Now, it's kind of a hard concept because it's hard to figure out how to put it into place, but this is just how it is. When there is a reaction that sometimes seems that it's decreasing the entropy, we have to look at it and how it affects the surroundings, and the surroundings will have such a reaction to that it keeps with the second law and doesn't actually decrease. Okay, so now we're going to move to Gibbs free energy. This is the last part of this section, and I'm going to read some of it, explain it. It has a very handy-dandy equation that you can use and will be given to you. So I want to make sure that you understand that it will be given to you. Okay, so Gibbs free energy, page 477. We can already determine the change of entropy of the chemical reaction as we learned earlier. The only other thing that we have to do is determine whether or not the reaction will really happen is to determine the effect that it has on the entropy of its surroundings, like we said before. This is relatively simple as well. Simple? So, the main way that a chemical reaction can alter the entropy of its surroundings is through the enthalpy. In a chemical reaction, if a chemical reaction has a negative entropy, change of entropy, it releases energy into the surroundings. Remember, if the product, if it's in the product, then it releases, in the chemical reaction, it releases energy. Alternatively, if a chemical reaction has a positive delta H, it absorbs energy from its surrounding, decreasing their entropy, and that would be in the reactant side. The value of the change of entropy will tell us about the change of entropy in the reaction itself. I lost my place. And the change of enthalpy will allow us to learn about the change in entropy in the reaction surrounding. So, there is a simple formula, and it's called Gibbs free energy. And it is delta G, which is Gibbs, equals the enthalpy minus the temperature times the delta S, which is the entropy. Okay? Boy, that's a lot to think about. So, the T in this is the temperature, and it's going to be in Kelvin. The Gibbs free energy can tell us whether or not a reaction is consistent with the second law. If it is, the reaction is called spontaneous, and you can proceed. If it is not consistent, then the law, to the second law of thermodynamics, we call it non-spontaneous because the reaction cannot occur. If the delta G is negative, it's going to be spontaneous. If the delta G is positive, it's not spontaneous and therefore cannot occur. This also is listed down here in your in your blue sections. It's green because I've highlighted it with yellow. If the delta G is less than 0, then the reaction is consistent with the second law of thermodynamics and is spontaneous. If the delta G is greater than 0 or is positive, then the reaction cannot proceed because it violates the second law. Let's look at equation 13.6 and see what that tells us. 13.6 is on page 477, but we're going to go to the next page. If a reaction is to be spontaneous, the delta G has to be negative. If the delta H is negative and the delta S is positive, the first term in the equation will be negative, and the second term is T times delta S will be positive. So, I'm skipping down. The two possibilities, we are looking on page 478 in what looks like your third paragraph. The two possibilities we just discussed are not only possibilities for a chemical reaction. Suppose the delta H of a chemical reaction is negative and the delta S is also negative. In this case, the first term in the equation 13.6 will be negative, but the T times delta S term would also be negative. This means that we would have one negative number subtracted from another negative number, and sometimes the result will be positive, indicating a non-spontaneous reaction, and sometimes the result will be negative, indicating a spontaneous reaction. In those cases, we have to calculate a value of delta G to determine whether or not the reaction is spontaneous. So sometimes it's saying you can't just look at it and figure it out. Okay, you have to work it through in accordance to a standard Gibbs formula. Look at 13.5 and you'll see what I mean. Standard Gibbs free energies formations are in kilojoules per mole. And here is a table of them. In the same exact way that we just did our previous examples, where we found the standard delta S and the standard delta H, the same exact formula applies. We have our table to help us figure out what the properties are so that we can subtract the reactant from the products. So it's just another table. That's why I let you look at go ahead and flip to page 610. 610, the last three are your standard enthalpies, then your standard absolute entropies, and then your standard Gibbs free energies. You're going to need these tables. No, you cannot figure out how to memorize these So go ahead and use these tables. Now, let's look at 13.7. Okay. In 13.7, it says, in example 13.3, turn that phone off. We studied the following chemical reactions. Here is, or the following chemical reaction. Here is your 2NO plus O2 produces 2NO2, and found that the delta H was negative 114.2. If the delta S standard is negative 147 joules per Kelvin, what is the delta G at 532 degrees Celsius? That is a lot of information, so let's put it all in order. What are we given? We are given the negative 1,142 kilojoules. I'm looking at it. And that is the delta H standard, okay? The second thing that we're given is the delta S standard, and that is negative 147 joules per Kelvin. And now we want to find our delta G standard, or just our delta G, sorry. And we have that it's 532 degrees Celsius, sorry. That's what I saw in my head, but my mind was thinking kelvins. So, let's see, can't see it that direction. Now here's what we have to do. First thing we have to do is convert the joules to kilojoules. Okay? Because right here, we need to convert these to kilojoules so that we can work the problem appropriately. Because what we found out is on table 13.5, the answer is going to be in kilojoules per mole. So we need to convert that to kilojoules. So I'm going to start my plan over here just because I have limited space. I don't have my big board. So my plan is going to be to convert kilojoules, convert joules to kilojoules, which would make negative 147 joules per Kelvin times 1,000 joules. That would make it 1 kilojoule. So the answer to this will be negative 0.147 kilojoules. Okay? So all right, did everybody see that? So first thing I did was convert because I need to be in kilojoules and not joules. The next step, let's see. Oh, it said here that my 532 Celsius is 805 Kelvin. That's helpful. Okay, having that information is super helpful. So now that I have all of that, I can use my formula, my delta G formula. So I'm running out of space. Let me use a different color. Maybe it'll help me differentiate. My delta G formula is as follows. I've got delta H minus temperature times delta S. Is that correct? Yes. So what I have here, my delta G, my delta H is negative. I wrote the wrong thing. Negative 114.2 kilojoules minus 805 Kelvin times negative 0.147 kilojoules per Kelvin. Now, what I can do here is start marking some things out. Okay? So I'm going to mark out my Kelvin here. So let's do first things first. This would be inside a parenthesis. So where's my calculator? 805 times 0.147 equals 118.335. Not kilojoules, negative 114.2 minus, now that's going to have a negative annotation on it, the negative sign on it, okay? So I'm going to go looking for my thing, negative 114.2 minus negative 118.4, no, I totally messed that up. Do that again, negative 114.2 minus negative, my thing just totally cleared out, sorry, negative 114.2. It still didn't pick up my negative. There we go. Minus negative 118.335 equals. So what that gives me is 4.1 kilojoules. My handwriting's getting bad down on this low end. Four kilojoules, okay? We're going to round that to the nearest whole number. So 4.1 would be 4 kilojoules. Now, let's see. Now, for your test, let's see. Sarah Jane, would you hand me that big white notebook right there on the couch? Playoffs. No, the big white notebook on top. Thank you. Whoops. Oh, Lord, the floor is far away. She says hello. Look how white you look. You look kind of green. Get off. Get out my camera. Get out my spotlight.
That's the most affection you've shown me in years.
Okay. The first 6 problems of your test are multiple choice, so that means you need to know some definitions. Look at the blue words. What is that noise? sun. I always try to do this when they're outside or when they're in bed, but I wanted to get it over with for today so I could do all the things I need to do. So here we are. Okay. Then you have some typical kind of questions, like if I have a container and it's hot, is that an endothermic or an exothermic reaction? If I have a container and it got cold, is that an endothermic or an exothermic reaction? You need to know if, when we talked about last week, you need to know if energy in an exothermic is in the product or in the reaction side. You need to know if energy is endothermic, is it in the product or the reaction side? Write balanced equations using energy formations. That means you need to, if I give you this number, if it's positive or negative, do I put it on the product side or on the reactant side? Kind of like let's see, find an example here. Oh, I think I'm missing some stuff. Boy, I am. I'm missing a whole page. There it is. For example, if I have a reaction, and I work it out, and in that reaction, I'm determining if it is an endothermic or an exothermic reaction, meaning that the energy is either absorbed or released. If it is a negative number, or if it is a positive number, then I would know that the negative number goes to the product and that the positive number goes on the reactant side. You need to know that when you're writing this out, because you're going to have to balance an equation and then write that number in. Let's see, what else do you need to know? You need to know how to do your Lewis structures, because one of your problems involves a Lewis structure. And it is not a difficult one. It's not one that's drawn out into eternity. It's very simple, but you still need to know how to do it. So if you need to refreshen your brain on Lewis structures, you need to do that, because one of your problems has Lewis structures in it. You need to be familiar with Hess's law and how to determine the delta H. I will give you the example for that. Your equation for that. You need to be able to find your delta S. There are two questions where you find, is it positive or negative, like what we talked about today, where it says find the sign for delta S. So you're going to look at the molecules and solid gas states, okay? One of your problems, you're going to need to find a delta S, kind of just like we did today. You're going to need your table for the delta S. And then you're going to need, the last one is you're finding a delta G. So you're going to need your table for the delta G to figure that one out as well. And that's basically it. You just need to follow your equations. I'm going to tell you which equation to use. You need to follow your equation and you need to follow your formulas, okay? Your formula tables. Basically, that's it. There's 15 questions. It counts as 23 points. And once again, use the app that I showed you or scan it and email it. I don't want these texted to me. When you text me a test or or you're on your own and all of that, what I have to do is go through and try to open up. I mean, I have to try to expand it on my phone, and it's just too hard to find. When you send me the test on scan by email, I click on it, I can open it up on my computer, and I can see a full vision of your page. Now, the grade that you get, it's not going to be on a sheet of paper because I am not going to print off every single one of your papers. I'm not going to do it. I'm going to grade it from what I can see visually. I can mark down on a piece of paper what you missed and why you missed it. I know some of you are going to want to know what and why you missed, and I'll mark that down for you to show you what you missed. And you can email, we can correspond that way. But I will not be printing these off and then sending you a copy of your graded work. Instead, I'm going to write your grade down. I'm going to mark on a sheet of paper what you missed, write the grade down, and put it in the grade book. It'll be updated as soon as I get them all. I'm not going to grade them here and there. I'm going to get them all compiled and grade them all together because it's a lot of work. It takes a long time. It takes a few hours. And so I need y'all to get those to me as soon as you get them done. And then like I said, I'll put them in a file. I'll grade them all together. They are due between the 10th and the 13th. Get them to me between the 10th and the 13th. You are doing school from April 6th through 10th. If you take that test on Friday the 10th, send it to me. If you take it on Saturday the 11th, send it to me. But I need it by 5 o'clock Monday the 13th so that I can grade it. I will not have a video for you on the 13th because we will be observing Easter week. We're going to take that week off. But I will be sending you a video on the 20th. And if we're in class on the 27th, we'll finish the last part of the module in class. But since we are already on a mandated 30-day stay at home, I seriously doubt we'll be back on the 27th. So I'll probably send you a video. I'll send you a video of that information, Dad. So I'll send you a video on the 20th and the 27th, and that will finish out chemistry, guys. So what we'll do at that point is we'll work on something after that. I don't know. Like I said, don't know if we'll be back in school. Don't know if we're going to come in for a week or two in May. Don't know what's going to happen, but we'll be finished. So letting you know, you have work due on the 13th. You have on the 20th, I'll send you a video, and we'll finish that Module 14 on the 27th, and all of your work for Module 14 will be due 1, 2, 3 on May the 4th. I'm looking at a calendar, but it's only April. April, yes, May the 4th. So all of work for Module 14 will be due on May the 4th. Clear on that. If you have to, I'll send it out in email form anyway, so you'll see that and your mom and dad will see that as well. But everything for this module will be due no later than 5 o'clock April the 13th. 5 o'clock, April 13th, Monday. So that's a week from the day that you get this video. Please send it to me. Please be prompt. Please be on time. If not, we're going to do it just like if you were to turn them in at school, and it'll be late, okay? So I think that is all. If you all need me, text me, email me, call me if you want to. I may not answer. Busy loud house, but we'll get through this last section here. We'll get through that last module, and you can mark chemistry off your list. So anyway, if you need me, call me. And I expect to be seeing some work starting to roll in between the 10th and the 13th. See you then.